Welcome to educator.com. In this lesson, we're going to be learning how to do prime factorization. First, in order to do prime factorization, we will learn how to factor numbers, and then we will create factor trees. Applications for this would be arranging items in a box or arranging people in an audience. A factor is a whole number that divides a whole number with a remainder of 0. So for example, factors of 12 would be 1, because 12 divided by 1 is 12 evenly. 2, 12 can be divided by 2 to get 6. 3, 12 can be divided by 3 to get 4. 4, because 12 divided by 4 is 3. 6, 12 divided by 6 will give you evenly 2. And lastly, 12. 12 divided by 12 is 1. So each of these numbers is a factor of 12 because you could divide 12 and get a remainder of 0. A composite number is a whole number greater than 1 with more than 2 factors. So for example, 12 is a composite number. You'll notice that there are more than 2 factors. A prime number is a whole number with exactly 2 factors, 1 and the number itself. For example, 2 is a prime number. The only factors are 2 are 1 and itself. Or 17 is a prime number. The only factors of 17 are 1 and itself. The special case is the number 1. 1 is neither a prime number or a composite. Because if you think about 1, its only factors are 1. Itself is still 1. So there are not even 2 factors, such as 1 in itself. So 1 is a special case. Prime factorization is when you write a composite number as a product of all the prime numbers. So for example, if I were to take 12, we know is a composite number, and write it as a product of prime numbers. Here we want to use a factor tree. I could break this down into 3 and 4. And 4 could be broken down as 2 and 2, a product, and bring down 3. And to write the prime factorization, I would start with the smallest number, 2. There's 2 of them, times 3. If you started off with 12 and broke it into 2 times 6, you would still end up with the same prime factorization. Once again, you have 2 times 2 times 3. So here we've written 12 as a product of prime numbers. 2 is a prime number and 3 is a prime number, and we've taken their product to multiply back up to 12. Divisibility rules are very good to memorize in order to think about how to break numbers down or to find factors. 2, if you can divide by 2, that would be any even number. Any even number can be divided by 2. And even numbers are numbers that end with a 0, a 2, a 4, a 6, or an 8. So for example, 20 ends in a 0, 22 ends in a 2, and so on. Those are all even numbers. You can divide by 3 when the sum of the digits is divisible by 3. So for example, 153. If I add the digits, 1 plus 5 plus 3, I get 1 plus 5 is 6, plus 3 is 9. Is 9 divisible by 3? Yes, it is. So I in fact know that 153 will also be divisible by 3. Goes into 15 5 times and goes into 3 once. 4. A number is divisible by 4 if the last 2 digits are divisible by 4. So for example, 124 I know is divisible by 4 because 24, the last 2 digits, are divisible by 4. A number can be divided by 5 when the number either ends in a 0 or a 5. So for example, 20 or 25. They both end in a 0 or a 5, and so therefore I know they're divisible by 5. The number, you could divide by the number 6 if both 2 and 3 work. And that is because 2 times 3 is 6. So if all the numbers for 2 work and all the numbers for 3 work, meaning can be divided by 2 and can be divided by 3, then you will be able to divide by 6. 9. The rule for 9 is very similar to the rule for 3. When you add up all the digits and it's divisible by 9. And lastly, you can divide by 10 when the number ends in a 0. Let's try finding some factors. A dance teacher has 12 dancers to arrange in rows of the same number at different times throughout the routine. What are the possible arrangements? Well, let's find the factors of 12. When you list factors, it's very easy to drop a factor. I think the best way to make sure that you don't drop any factors is to put them in pairs. So for example, 1 times 12 will give me 12. Next, 2 times 6 will give me 12. 3 times 4 will give me 12. And here I see that the factors have all met. 5 and then 6. So this way I know that I've caught all the factors. So what are possible arrangements? So one student in 12 rows, or 2 students in 6 rows, or 3 students in 4 rows, or 4 students in 3 rows, or 6 students in 2 rows, or all 12 students in 1 row. These are all the possible arrangements. You have 20 oranges to put in a gift box. Each row must hold the same number of oranges. How many oranges can be in each row? So let's find our factors of 20. 1 times 20, 2 times 10, 3 does not work, 4 times 5, and there we've met in the middle. So possible arrangements are 1 orange in a row, 2 in a row, 4 in a row, 5 in a row, 10 in a row, or 20 in a row. Let's decide whether these numbers are prime or composite. Using my divisibility rules, I know that 48 is an even number because it ends in an 8. I also know that 48, these last 2 digits are divisible by 4. So already I've named 2 factors outside of 1 and 48, 1 in itself. So I know that this number is composite. 53. Well, let's run through our divisibility rules. It's not an even number. It doesn't end in, when I add 5 plus 3, that's 8. That's not divisible by 3. The last 2 numbers, 53, are not divisible by 4. It doesn't end in a 0 or 5. So it doesn't look like any of these rules are working. So let's call it prime, because the only 2 factors are 1 and 53. 57 looks like a prime number, because it's an odd number, and a lot of times numbers ending in 7 are prime. But always make sure that you try the number 3 and 7 before you decide a number is prime. So let's try 57 divided by 3. Goes in once, and 27, 9. So in fact, 57 is not a prime number because it has factors of 3 and 19, more than 1 in itself. So this is a composite. So remember, before that you decide a number is prime, based on just the way it looks, run through some of your divisibility rules. Find the prime factorization. And remember that you should put the factors in an ascending order at the very end. So starting with 42. There are a lot of different ways you could start out. You could say 2 times 21. I'm going to begin with 6 times 7. This breaks into 2 times 3, and this is 7. And now I've reached all prime numbers. And I want to put them in ascending order, so the smallest number first. So the prime factorization of 42 is 2 times 3 times 7. Now let's try 84. Maybe off the top of your head you don't know all the factors of 84. You could always decide that 84 is an even number and divide by 2. So half of 84 is 42. And then at this point you could see 6 times 7 and 2 times 3 and bring down the 7 and bring down the 2. It's a good idea to bring down all the numbers so that you can look at them straight across in a row. You're going to use exponents when possible. So it's 2 times 2, so that's 2 squared times 3 times 7. Now we're going to go backwards and, or the other direction of prime factorization, and we're going to multiply all the numbers. We're going to find the product to find the number of this prime factorization. So written out, it's going to be 2 times 2 times 2 times 5 times 11. 2 times 2 is 4. 4 times 2 is 8. 8 times 5 is 40. And we're going to multiply that with 11. 0, 4, hold the place, and 4. 1 times 0 times 4, hold the place, 1 times 0, and 1 times 4. So 440. 11 times 4 is 44, tack on the 0. So this prime factorization equals to 440. Let's multiply this and find the product. 3 times 5 times 5, I'm expanding the exponent, times 7. Sometimes, remember from order of operations that we do not need to multiply numbers in order. We know that from the commutative property of multiplication. 5 times 5 is 25. And 3 times 25 is 75. And lastly, 75 times 7, 49, 50, 51, 52. So this equals 525. You could go in order too and say 3 times 5 is 15, and 15 times 5, and then times 7, and so on. Is the number 93 prime or composite? Explain. Well, in looking at 93, I'm going to try the divisibility rule of 3. I know it's not an even number because it ends in a 3, but the divisibility rule of 3 tells me if I add the digits and I can still divide by 3, 3 is a factor. 9 plus 3 equals 12. And 12 can be divided by 3. So I know that 93 can also be divided by 3. 3 goes into 9 3 times, and 3 goes into 3 once. Now at this point, just because I found one extra factor, I already know that this number is a composite. I know it has the factors of 1 and itself, and now I found an extra one, 3. So at this point I can stop, and I know that 93 is a composite. And asked to explain composite because 93 has more factors than just 1 and itself. Or perhaps you could say something like composite because 93 also has the factor of 3. Find the prime factorization of 72. Let's take 72 and break it down into 8 times 9. A lot of times it's good to do prime factorization with two numbers that are close in value rather than doing 2 times 36. But it really doesn't matter. Each way you're going to come up with the same answer. 2 times 4, 3 times 3. Bring down the 2 so we can have everything in one line, and 3 and 3. Now let's use exponents and write it in ascending order. It's 2 to the third power times 3 to the second power. A group of 36 Boy Scouts are marching in a holiday parade. When they march, they must form rows of equal numbers of Boy Scouts. What are the different marching arrangements? So for this holiday parade, they could set up a lot of different looks for their organization. And let's find out all the different ways that they can be lined up. So the factors of 36. I'm going to list the factors. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 doesn't work, and then 6 times 6 meets itself in the middle. So these are all my factors of 36. Remember that it's very helpful to pair the numbers, such as 1 times 36, 2 times 18, in order to make sure that you don't drop any factors. So the different marching arrangements are 1 row of all 36, or 2 rows of 18 Boy Scouts, or 3 rows of 12 Boy Scouts, or 4 rows of 9 Boy Scouts, or 6 rows of 6 Boy Scouts. You could also do 9 rows of 4 Boy Scouts, or 12 rows of 3 Boy Scouts, or 18 rows of 2 Boy Scouts, or 36 separate rows of just 1 Scout deep. So these are all the different arrangements. Remember not to stop here because the first number is representing your rows and the second number is representing the number of Boy Scouts in each row. And the question does ask you to come up with all the different marching arrangements. Sarah is planting 36 bunches of daffodils in her garden. She wants to put them in rows of equal numbers of bunches. What are her options for arranging them? So let's come up with all the different ways that we can get 36. 1 times 36, 2 times 18, 3 times 12, 4 times 9, 5 doesn't work, and 6 times 6. So we meet in the middle. Remember to use pairs so that you don't drop any of the factors. So for example, 1 times 36, 2 times 18, and so on. So the different ways that we could line up these daffodils. Let's call our first column the number of rows, and our second column will be the number of daffodil bunches. So we could have just one row and all 36 are lined up, all 36 bunches of daffodils. Or we could have 2 rows and each row will have 18 bunches, or 3 rows and each row will have 12 bunches, 4 rows with 9 bunches, or 6 rows with 6 bunches. Or we could have 9 rows with 4 bunches, 12 rows with 3 bunches, 18 rows with 2 bunches each, or 36 separate rows with 1 bunch in each row. So these are all her different options. Probably the best option if she wanted a square would be the 6 times 6, but she might want to have a different design in her garden. Thank you for watching educator.com.